Thank you. Thank you. I feel as if I'm here under slightly false pretenses in that I've never thought of myself as a historian of mathematics. But of course, as a historian of science in general and of physics in particular, mathematics and history of mathematics has been important at various stages in my work. And I think I'm here primarily because Ursula Martin had got involved in some of my work on histories of artificial intelligence and then asked if I could give a contribution here, maybe talking about what I did on climate change. And it's still not clear to me how much of what I did on climate change actually relates to the history of mathematics. But I'll attempt to address that in the course of this talk. It will be very much, rather than a contribution to the history of mathematics, a contribution to the history of mathematization of the empirical climate sciences. And that contrast between the history of mathematics, which is often the preserve of historians of mathematics, and the broader question of the history of mathematization is, of course, one of the interesting productive tensions between the history of science and the history of mathematics. In my training as a historian of science, there was one really powerful example of the ramification of mathematics in different realms through the study of the Laplacian program in a key paper by Robert Fox, published as long ago as 1974, which studied how in post-revolutionary France, celestial mechanics also became a model for microphysics, which gained wide purchase through a canny use of institutional power and prize giving, but was vanquished due to the rise of a new generation of scientists using different mathematical tools to approach phenomena that also proved somewhat recalcitrant to Laplacian methods. And this was also a very powerful story about the relations between mathematics and institutional power in this post-revolutionary context where there was so much change in France. It's perhaps not accidental that Laplacian physics was overcome in different areas by wave models of light and by Fourier's studies of heat propagation and the development of spectral analysis. Now, historians of mathematics might also see later episodes in the history of celestial mechanics in Poincaré's approach to the three-body problem and chaos theory, as this was revived by Lorentz in the middle of the 20th century, and as well as in the use of techniques initially developed in celestial mechanics in new contexts in quantum mechanics, getting back to microphysics in different ways. But today I want to study a much less conceptually remarkable example than those two, but nevertheless one that offers a fair bit of insight into processes of mathematization. I've enjoyed lots of really interesting papers in this conference, and I'll continue the frameworks that two of them have offered in particular. One is the way that Megan Breer examined the information order of particular archives and the institution of the Royal Greenwich Observatory. Though in my work on archives, I'll be more focused on the work practices of an individual in collaboration with others than on the question of who gets to visit the institution or whose writing is included in the archive of the institution. So there's a slightly different focus there. The second model I'll pick up from the papers that we've heard over the past few days is Michael Barani's methodological reflections on studying relationships within the mathematical community at different scales, where he exhorted us to pay attention to institutions and infrastructures as well as mathematical implications, and to problematize shifts between mathematical community or collaboration at international intercontinental, and global scales. I'd invite you to consider the physical example that I'll be studying today to see how an extraordinarily global argument about how the relations between the sun and the earth can explain the ice ages that the earth has experienced in the last 2.5 million years through a close study of 2 specific deep ocean sediment cores by a British man and 2 Americans making arguments about northern hemisphere ice masses and subantarctic ocean temperatures and water structures. So I'll be exploring a physical analogue to the community study that Michael had shown. Now, generally, our relation to, or our avenue to the study of climate sciences and mathematics has been through an approach to climate models and to the relations between climate science and politics. Climate models were technically developed as an extrapolation from the practices of numerical weather forecasting by computers generated after World War II, working out how to run those weather forecast models for the Earth as a globe and over much longer time periods, first using models of the atmosphere and then linking those to oceans, Earth systems, and later the carbon cycle around about 2000, and linking them to socio-economic models of the effect of fossil fuel and carbon dioxide on the temperature at different stages through this process. Instead, I'll be looking at Milankovich's mathematical theory of climate, which is surely one of the most important underpinnings to our understanding of the ice ages. But I won't be focusing so much on Milankovich's work itself. Rather, I'll be exploring how it was demonstrated empirically, studying 1976 Pacemaker of the Ice Ages Pacemaker of the Ice Ages paper that was widely taken to confirm Milankovich's hypothesis. And I'll be looking at it both as another episode in the long-term history of the relations between celestial mechanics and the physical sciences, and for what it reveals about the many different ways that climate has been modelled. But I'll be more concerned with the general features of those models than on the particular elements. Reflecting on the work of a project that I've been involved in called Making Climate History, I will approach the collaboration of James D. Hayes, John Embry, and Nick Shackleton, along with Nick Shackleton's research assistant, Michael Hall, as one instance of long-standing searches for cycles governing relations between the sun and the earth. Something that was particularly taken up by a couple of mathematicians in this period, Andre Berger being one of them, and Ananda Venanker being another. We'll be considering how the models of time that the experimenters developed may help them make sense of sediment cores deposited over hundreds of thousands of years. And this is an account of how the imprint of sun and climate, sea temperature and sea level were found in sludge, composed largely of the tests of foraminifera, which are a unicellular creature that live on the sea surface or on its floor. Their shells are often about 1 millimeter in diameter. And when they die, those shells drift to the floor and form sediment. And the chalk cliffs of Dover are composed of organisms like that. So that's my subject matter. And the last thing to say about unpacking all the different terms of this title is that I'm much more diffident now about my ability to give any lessons. I will rather show some connections and hope maybe that you'll draw out the lessons that are appropriate to this. Perhaps we could see this as another example in what Kutcher was talking about in the relation between freedom and control. I'm insisting upon your freedom and your better ability to interpret this material than my own. So I want to begin with a bit of an investigation of the historiography of the climate sciences to make one major point that I think is really quite similar in considering the climate sciences and the history of mathematics. In both cases, scientists and historians write those histories. Scientists and historians write the history of climate just as both mathematicians and historians write the history of mathematics. But there's a subtly different character to work on the climate sciences because the histories of climate have been written for scientists by historians also, and to contribute to the further development of the science. And this is unusually true in the case of histories of climate by historians of science. They're very much more closely oriented towards developing climate in both technically and in the public realm than is typical of history of science. And I'm not sure how characteristic that is of mathematics. Generally, that endeavour is really valuable and a lot has been achieved through it. But one feature in which climate sciences are very different from mathematics, generally anyway, is the extent to which they have been contested, also by scientists, although admittedly by a much smaller group of scientists with different socioeconomic goals, and the public debate about the status of the climate sciences has also marked the character of the historical work written on the climate sciences. And that's been good, and it's also had its limitations, I think. Now, if we look at this things, I want to make a couple of points through this series of valuable books. The first is made by the one on the top here, Ice Ages, Solving the Mystery, written by John Embry and his daughter Catherine Embry, published in 1979 to provide a historical context for the Pacemaker of the Ice Ages paper that had been published just 3 years earlier. So the history of mathematics, the history of climate, often comes first through scientists. And it's a public affair. It's bringing their science into the public. Our first major history of the discovery of global warming came from Spencer Witt in 2003 at the American Institute of Physics. And that's a very interesting book, and it's formally interesting too. It was one of the first hypertext histories published in print and online at the same time, and using a form of timeline and capsule information that you could expand into discussing any of the around about 1,000 papers that he was discussing in his account of the history of the climate sciences. One of the most important things about the story of the climate sciences, he thought, was it gives you a model of climate change, a model of science that is radically different from the kinds of models that we've got by focusing on physics or even on astronomy or other areas. The discovery of the pertinence of human global warming came 180 years after the problem was first approached. And we know now that it's still hotly debated. And so he thought you needed different methods and different forms of understanding this area of science because of its complexity and because of its relation to the social world. And that's, I think, really important. Moving on to the next studies that I want to focus on, climate's histories have very often been written in order to understand the public debate and the role of a few key contrarian scientists within that public debate. And in this really important book, Naomi Oreskes and Eric Conway showed the think tank infrastructures that enabled a few scientists to effectively challenge overwhelming consensus by most of their peers on the public stage. And if one seeks to understand the causes for that, then it's very clear that their socioeconomic views were really important in that. They were, in fact, entirely oriented around questions about the contrast between freedom and control. And they saw economic freedom to be paramount and intellectual freedom to also be important in approaching the funding-driven climate sciences that were intent upon governing and regulating the world. They interpreted very much in similar terms to the ones that Katja was talking about earlier. And one of the things that's most interesting about this is that despite giving an extremely pertinent blow-by-blow account of climate skeptics and showing how contingent their views were and how much they depended upon particular sources of funding and the like, Oreskes and Conway end up with a model of the relations between science and politics that is very similar to the model of the relations between science and politics that the climate skeptics hold and that the IPCC holds, which is that climate science is good science and what the skeptics are doing is bad politics. And separating the two out in that way, in the ending of their book, I think is a very important but subtle problematic that hasn't fully been coped with in the way that we've approached this area. The other thing that's been remarkable about histories of climate has been their focus upon climate models. And those models I mentioned earlier stem from meteorology. They reflect the computerization of the study. They've been extremely important. As I'll show you soon, in the collaborative work that I've been undertaking, we've looked to another side, to the empirical climate sciences, rather than climate models. But this is a wonderful book that offers a kind of historical sociology of the development of climate models, and also was developed in close consultation with the scientific community, in particular with the relationship between Paul Edwards and Stephen Schneider, an important climate scientist. But in looking through all of these, I want to finish with two quick points. One is that we should include the debates and discussions and books of climate science denialists in the way that we approach these questions. And I highlight this one here, Why Scientists Disagree About Global Warming, because it's a direct, sustained attack on this book here. It was published in 2 different editions. It's not very impressive, but it's been distributed to 30,000 teachers and legislators in the United States. So if you want to understand why US politics and views about climate look different, you really do need to take account of the important means through which these groups have purveyed their views. And then the final paper I'd like to return to is this one here. Notice that it's by Matthias Heimann and Amy Dahan-Delmedico, important climate science historians and a historian of mathematics in Amy Dahan-Delmedico. It's on epistemology and politics in Earth system modelling, historical perspectives, and it's published in the Journal of Advances of Modelling, in Modelling Earth Systems, in an Earth Systems journal. That's another illustration of just how important it is to link the science and the history in this particular period. And I want to note what it says about the 1970s, the period that we'll be going into detail in this talk. They say that climate modelers in the 1970s, who had operated largely ignorant of and undisturbed by environmental concerns during the 1950s and 1960s, experienced a deep cultural shift during the 1970s. The idea of impending risks about future changes of climate, though believed to occur potentially decades ahead, introduced a new massive challenge: the politicization of climate science, with increasing demands to investigate climate change and serve politics with long-term climate prediction. And that's their analysis of the 1970s. Climate models realised they had to make their subject political. I think one of the things that's interestingly limited about that way of framing it is seeing it to come from environmentalism, from a social movement. And I think we'll need to look more deeply into the relations of practice in the period, and that's one of the things that I'll be looking at in my own work here. They go on to talk about the way that a new and younger generation of models than those who pioneered the study in the 1950s and 60s, people like Stephen Schneider and James Hansen, propagated a strong language of concern about future climate change from the early 1970s, writing that they helped move the art and science of climate modelling toward the art of prediction, the goal of prediction, in order to inform society about the potential threats of future warming. And they write also that in this period, climate science went public. Schneider and Hansen proved pioneers, they write, in addressing public audiences with alarming claims to raise political attention. Now, in a way that's true, and the level of alarm was probably more serious in 1970s than earlier. But I'd say that, in fact, that process of the climate sciences going public has occurred throughout the entire period. It's just been in different terms, and the politics of it has often been there, but not so readily visible. And we'll see that in some of the work that I want to do now. Now, I want to finish this rather long historiographical discussion by returning to Amy Dahan Del Medico and an article that many of you might have read that she wrote on mathematics in the 20th century in 1997 for a wonderful book on science in the 20th century. And her concluding paragraphs are interesting and salutary. She writes that two conclusions can be drawn from her survey of mathematics in the 20th century. Firstly, today nothing seems likely to put a brake on the expansion of mathematics and its interface with a range of human activities. And I think that has definitely proved prescient. That's certainly true. There's been an extraordinary mathematization of life. Secondly, she said, mathematics, whose purity is so often appealed to, has nevertheless been subject in a particularly brutal way to the shock of factors which were a priori external to it, and in particular the major political dramas of the century in the emergence of Nazism, the Second World War, and most recently the collapse of the Soviet Union. I think now we're learning to see that the question of politics of mathematization needs to be studied really within the field, and the link between the internal and the external needs to be examined really closely. So that concludes my historiographical overview of the framework in which we developed our project on making climate history. And what we wanted to do was do something that we thought most histories are not doing. Most histories are focusing on the relatively recent past and looking towards what will come. That's certainly true of the Oreskes and Conway book. We wanted to look at the history of making and knowing climate change over the entire period that it's taken to remake the climate. That is from the Industrial Revolution through to the present day. We split it up in 5 different work packages led by different people. We had a whole group of postdocs, and partway through the project we shifted our aims towards making a book. We'd wanted to make a book all along. We chose the subject matter of the book. It would be the construction of global temperature as the key climatic index. And we've developed 15 chapters in 3 parts, organised roughly chronologically. You can see there that the first part looks at what we call thermal fieldwork, the second part at the period from 1850 to 1920, waters and empires in the period of high imperialism, and the third part, making temperature global, the period that I'll be looking at today. And I'll be looking at a particular area of that, while my colleagues Sarah Dry and Mike Hume have been focused on temperature series and the instrumental record, and the way that that's been understood. I've been looking at paleoclimate, climate in long-term history. And I want to take you today through some episodes in the emergence of paleoclimatology, where we'll see curves and curve matching as being an important goal. And I'm sure that's been important to historians of mathematics in different ways. And these particular episodes got underway very much at the conclusion of World War II. And this is a revealing photograph of Harold Urey, and behind him Cesare Emiliani. Urey was the person who developed the possibility of using isotope ratios incorporated in shells and bones and things like that as a register of temperature, by noting that the isotope take-up is dependent upon temperature. That you take up more of the heavier isotope at high temperatures than at low temperatures, and therefore you can use material objects as a register of temperature. And we'll see he sought to do this in deep time. I want to note before moving to that what was important in this was a mass spectrometer. This mass spectrometer was developed by Alfred Neer of the University of Michigan, and revealingly importantly, this is one of the ways in which the politics gets hidden in this period. He said that in the period before World War II, mass spectrometers were mostly used in petrochemical firms. Afterwards, they were used a lot in physics. And what Urey did in showing this form of making determinations of temperature change and age over time was taken up in lots of different places, and we'll explore some episodes in that in the course of our work. And the person who was instrumental in that, Cesare Emiliani, interestingly and importantly, was trained as a petrogeologist in Italy before coming to Chicago and taking up the study of foraminiferas, the sea creatures that I mentioned, and bringing that into the techniques available to Urey's kind of analysis. So let's explore what Urey showed, and one of the first major examples of using this historically. Urey did a study of layers in the shell of this belemnite sample, which he knew to be roughly 150 million years old. And isotope analysis showed that there was a temperature variation. You could pick out seasons over the 2.5 years that shell lived. That's extraordinary, isn't it? There's a wonderful curve, right? And it's interesting and important to note that he picked out on belemnites, and 150 years ago, belemnites because he thought they'd be amenable to this kind of study, 150 million years ago because that's when the dinosaurs died out, and actually he had geological aims. He was trying to work out a climate history, even in this very early work. As I said, Emiliani took up the same technique in looking at foraminiferas. And he knew foraminiferas were important because foraminiferas were very important in petrochemical discovery. They helped you work out where horizons of oil were in the mines that you in the cores that you dug in the earth. But he was looking at it in sea sediments in particular. And here's an illustration from a science article, once more showing, a Scientific American article, once more showing how this is always public. And that's the core that he's using. And this is a temperature curve. He thinks that he's finding the sea surface temperature of an organism that lives on the sea surface, and that he can trace it over, that's now back 50,000, 100,000, 150,000, 200,000 years. And he can trace a common curve. He's matching curves in cores from the Caribbean, and he's pulling out a common story. It's amazing that he finds a common story, and that leads him to think that there's a general technique here, and he actually thinks that he should perhaps be able to match this to Milankovitch cycles and provide some clue towards the possibility that Milankovitch cycles do determine the ice ages. One other page from that document, from that paper, this gives a time history of land emergence and of sea level change over time, relating it to different organisms in different periods. And that's to make the point that these studies were integrated into historical geological work. They were a climatology in a very long time span, and they were integrating it into, in that case, species, in this case, human evolution. So really quite big social claims are being worked out here, and a very important and interesting interdisciplinary piece of work emerging. So this is the work of Urey and then Emiliani, who moves from Chicago to Florida and starts developing this as an oceanographic study and becomes well known as the father of paleoclimatology in oceanographic work. Another context in which this was developed importantly was in Cambridge, where a sub-department of quaternary research, that's of the last 2.5 million years, was founded in the Department of Botany after the war to pick up a Fenland research group that had begun from the 1930s. This is them on an excursion to the East Anglian coast, picking out crag formations, and they note that in 1961 they got a grant from the Department of Science and Industrial Research to enable the first steps in the establishment of a mass spectrometric lab. They want to explore radiocarbon and measure paleotemperatures by means of oxygen 1816 isotopic analysis. That technique, conceived by Urey, developed by Emiliani, should provide information concerning the temperatures that existed at the time of the growth of foraminifera in these crag deposits. So it's being integrated into terrestrial geology. The big difference between terrestrial geology and what you can find in ocean sediments is that terrestrial geography is really patchy. You've got some clear layers here and then nothing. And in the ocean, you have the prospect of looking at hundreds of thousands of years of sedimentation that's been undisturbed. You've got an extraordinarily different record. The curves, you can draw curves there so much more easily. So you can see the wonder of this new empirical area. So Nick Shackleton was taken up as a research assistant, published his PhD in the course of his work there. Here's an image of him on shipboard, and he went on ship before he published his PhD. That's to make an important point about the sociability in this area. They were oriented not just about their lab work and libraries, but about experiencing common work on the ship. And every year, between 10 and 20 scientists would gather on shipboard and spend a month together or more on shipboard, gathering cores and working together in that context. Here's forams that he's going to pick, pulling out different forams. Here's a slide he uses to do that. I'm not showing an image of his mass spectrometer here, but the key thing that Nick Shackleton did was develop a mass spectrometer that could use tiny samples in comparison to Emiliani. And we'll see why that was important shortly. The major reason is that Emiliani had been looking at planktonic foraminifera who grow on the surface of the sea and then die. And there are much smaller numbers of foraminifera that grow on the sea floor. And Shackleton knew that the conditions on the sea floor are likely to have been stable in temperature, not to have oscillated as much as the sea surface. So he was suspicious about the kind of curve that Emiliani had drawn. And he wanted to test that with benthonic foraminifera, but to do that, you needed to be able to take 5 or 6 samples rather than 30 or 40 or 100 planktonic foraminifera, because there were far fewer of them. So he needed to develop a different kind of mass spectrometer. Now let's look at 2 key arguments that brought a time scale into this study and managed to compare insulation spectra and climatic spectra. How did that occur? So I'm going to go now into the information order of the archive. In the Nick Shackleton papers at the Royal Society Archives, there are an enormous array of boxes, and I first saw them before it was catalogued. So I saw the working arrangement that he used, and he had a file for a core. And in that file, you'd find a page which gives, or many pages which give a physical description of each core. This is not the raw data, but the averages of measurements. And this is something that comes from another scientist, which is a diagram of species abundance and extinction from a botanist who's working with the same sample. So you get lots of different work and a register of interdisciplinary work in the things interleaved into these papers. What he wanted to do with this particular core was to provide a timescale. And to provide a timescale, he needed a sediment core that would go back to the point where the Earth's magnetic field flipped 700,000 years ago. And he knew there was one that could do that, RC 11209, and he asked for that core from the Lamont Doherty Geological Observatory, and were told that that core had been sampled so many times by other people that although it had the kind of length he wanted, there wasn't enough of it to do the study of. So he used instead a core that's now become much more famous, V28238. That was from the Vima's 28th voyage. It was its 238th core drilled on that voyage. And the argument that he did involved a very sophisticated set of curve matching. And I want to show that in these diagrams here. First of all, perhaps, the length of the core. This is depth in centimetres. So that's 12 metres, that's 16 metres. There's the magnetic flipping. And the fact that he has a core where he can get a constant record over that gives him the timescale that he wanted. But he also developed arguments about the relations between planktonic and benthonic foraminifera. And that's this matching curve here. One of those is planktonic foraminifera, the organisms that grew at the top of the sea. The other is of organisms that grew at the bottom of the sea, and they showed the same curve. So it wasn't temperature that was being reflected here, it was a different climatic index. That climatic index was the water composition. And the water composition is shaped by how much ice has been melted into the sea. So in fact, it's a direct measure of sea level, in a way much more directly important for climate work than the temperature measurement. So that was a very important argument. And then the other curve he matched was he took these two curves are from different cores, the core that he studied, which is in the Pacific Ocean, and a core that Emiliani had studied in the Atlantic Ocean. And he shows that their curves match too, not in amplitude, but in where the peaks occur. So he does think you can curve match in the way that Emiliani had thought, but the significance of the curve is different than Emiliani had thought. So he's making arguments about sea level, not about temperature. And here's the acknowledgements from that paper. NJS is most grateful to M.A. Hall for operating the mass spectrometer with meticulous care over long periods. Thanks other colleagues in a group at work called CLIMAC we'll look at soon. And Cesare Emiliani, the Italian, and Richard West, the leader of the sub-department of Quaternary Geography. I just want to note Mike Hall. Mike helped him revise his mass spectrometer, and when Shackleton took a sabbatical in the United States in 1974, his technician went with him. And his technician spent the year there and refitted 3 different mass spectrometers in other climate labs and got a job offer from one of those climate labs. Emiliani took him out to a Florida nightclub with topless waitresses, hoping that would persuade him to leave Cambridge. It didn't. And Mike Hall then also made the shift from being a lab technician to being a research scientist. And when he made that shift, he had to change union in Cambridge, and he got agreement from the technicians' union that he could stay in the union even though he was no longer a technician. And he changed the tea time of research staff and technical staff to be the same, so that the whole lab would meet at the same time. So we can see lots of interesting ways in which work practices are reflected, and he became a co-author with Nick Shackleton from 1979. He's co-author of 38 of Shackleton's 313 scientific papers. So we can really see people crossing these boundaries in this period in the 1960s and 1970s of great social discord, of course, in the United States and in Britain. One of the implications of the work was carried out in CLIMAP, which was a project to provide long-range climatic maps of sea surface at different times. And this was probably their most important one, of the sea surface of 18,000 years ago in the Northern Hemisphere summer. And you can see here the outline of Australia is much bigger, right? There was much less water in the oceans then. And there were enormous ice sheets. These are ice sheets here, and this is snow cover over the United States and Northern Europe. This is the peak of the last glaciation. And technically, they were able to do this because of the time scale that Shackleton and Opdyke had provided, which meant that they knew they could work out when 18,000 years ago was, because they could curve match their own curves to those curves. The second argument that I want to look at is the argument that's now much more famous about variations in the Earth's orbit, Pacemaker of the Ice Ages. And that's the paper published in Science with 3 authors, Hayes, Embry, and Shackleton. Hayes being the person who managed the library of cores in the Lamont Doherty. Embry being a geologist and mathematically inspired geologist. Shackleton working on the forams that I've described. And when Shackleton died, one of his colleagues, Phil Gibbard, wrote in their now classic paper, Hayes et al., were able to identify 3 periodicities of changes in the Earth's orbit, the so-called astronomical cycles of 100,000 years, 41,000 years, 23,000 years. That's eccentricity, this is obliquity, and this is the perihelion, finding them in the sludge. Extraordinary. So how did they do that? Here's a diagram of the core location. What they needed was cores that gathered sedimentation really quickly so that they would have a lot of resolution. Now, you might have noticed that 1 inch in a core might be 1,000 years. So you need really a big core to be able to get to fine resolution and to deal with 20,000 years. They needed a very fast rate of sedimentation. And they needed that to be undisturbed. And there were only 2 cores they knew that fitted that criteria. They were from the area between South Africa, Australia, and Antarctica in the Indian Ocean. And they needed to use 2 curves because one of the curves was a bit imperfect. The top was missing. These are that's a recent photo of Globigerina bulioides. They were studying a planktonic foraminifera because Shackleton's been able to show that they're the same. And then Radioluri, Cyclopedophora davisiana, another species, and they developed a lot of different intersecting arguments. One of their argument was about northern hemisphere ice, right? So in the deep southern hemisphere, they're making an argument about the northern hemisphere. This is intercontinental in a different sense than Michael was talking about. And other arguments are about sea surface temperature using the radiolurians and about the structure of the water in that core too. Here's the image that tied everything together. They show here spectra of orbital and insulation variance as they got those from the work of Andre Berger and Anandu Vernakar. And they found that those interpretations of celestial mechanics and Milankovitch's cycles didn't vary within 1,000 years over the last 400,000 years, but over a longer time span, you had to prefer Berger's work because it included higher order terms. And they were comparing the insulation variance with frequency with climatic data variance, and they show a sea surface temperature measurement, the oxygen isotope measurement, that's the sea level one that we saw before, and then percentage of Cyclopedophora davisonia in these diagrams. And they found a big peak in 100,000 year cycle, which isn't a big peak in the orbital data, but 2 big peaks in 43 and 23 roughly cycles, which did match those. And that sets out an investigation of the different components and the structure of this complex causal picture. And one of the things that becomes clear when you go into the folders that are in the Royal Society is that there was a very important correspondence between these 3 different men and a wider group. And here's one letter from that correspondence. It's from John Embry to Nick Shackleton. probably in May 1976. He says, I feel there should be a footnote stating the identifications of Emiliani and Geiss and van den Heuvel's chronologies for the record. The thing about those earlier chronologies was they'd all been different. And now you could give one chronology. And he says, and we'll draft one up for the possible insertion in the classic manuscript. This was designed to be a classic paper. It was not later recognised to be a classic paper. And that's one of the interesting things about this particular source and this paper. You see the communal work they did to make sure it could be a classic paper. And that was by sending the work to a group of about 8 or 10 different scientists and getting comments on it and the like. It goes on to talk about their stances in comparison to what other people have thought. This is before the publication of the paper. When the paper is published, I'll just show you once more the acknowledgements, footnote 83, and it talks about data generation, and there are 5 names there, 2 of them being the celestial mechanics, 1 of them being the spectrometer, and the data processing, 5 names there also, with JZ Imbry's son, and then also 3 people who helped with the production of the manuscript. So this is an intensely collaborative piece of work. And then they talk about the people they sent it to, and interestingly, this list is smaller than the list that we know they actually sent it to. So you can track the community dynamics in this. Out of this came more work in celestial mechanics, and that's illustrated in Andre Berger, who published a paper in Nature saying, we've got support for what I was talking about now, and then published an extended paper in celestial mechanics, and he went into work on climate modelling and was involved in early Earth systems climate modelling. And as I told you before, the first historical account of this emerged from John Imbry and Catherine Palmer Imbry in 1979, just 3 years after the original paper. And it's interesting too that they think this is a different kind of science, and they offer a timeline at the end of their book, but their timeline actually differs from the timeline that Spencer Wirt had offered. Spencer Wirt offers a timeline of discoveries. Their timeline also talked about when you stopped believing in something, about when theories were no longer felt to be pertinent. And that's one very interesting thing to emerge from this, but his book is mainly about timescales, and it's mainly about curve matching and telling the story about ice, but he neglects the story of human change and species and so on, and petrochemical work that we saw, you can see in the work of Emiliani. So there's things disappearing from the record too, in the way that this account is developed. Now I want to finish with one diagram which represents this work from 1990 and the first assessment report of the Intergovernmental Panel on Climate Change. And the first thing to note about this is that they have a chapter on observed climatic variations and change, and it's chapter 7 after 6 chapters on modelling, where you've got data, but it's all already incorporated in it, right? And there are about 5 or 6 pages on paleo data. But when they do their paleo data, they call this, which is actually the curve you saw from Shackleton and Opdyke, they call that temperature, which it wasn't. And this one, they say is a global temperature variation, but the person who drew this diagram thought that diagram was a Central England temperatures. And that shows the imperative of globalization of temperature. That was important for the IPCC in 1990. So in some ways, it's a direct representation of the point that Heyman and Delmedico had made. And they finished their work by saying that now We're seeing a globalization of the climate problem. It's becoming important to everything we look at. We have to relate everything to climate. And we're seeing a climatization of the world by actors who present issues formerly unrelated to the climate regime, now through a climatic lens. So we're seeing a very interesting set of dynamic issues here. Thanks for your attention.
So thank you very much for this wonderful talk. Of course, the result of global warming is that in England we have Italian weather in the last 2 months, so we are very happy about all these diagrams, how they are better. So we have 4 minutes for just a few questions, or perhaps one question. Let's see if I can pick a question. No.
I see one from Katja.
Yeah. Of course. Sorry, please.
Thank you, Richard, so much. I wonder if you could say a little bit more about those collaborations. You know, you mentioned infrastructure, and we were thinking about infrastructures a lot, thanks to Michael. Could you just say a little bit more how those collaborations happened? What elements of research infrastructures allowed for those collaborations? What were the challenges for the people to, it's easy in the 21st century to start collaborating on a paper for, I don't know, 7, 10 different people. But in the 1970s, I imagine it probably was different.
It was different. It wasn't necessarily too difficult as far as these people were concerned, right? They always mention their funding. They got a mix of NSF and ONR funding for this work. The core work was also funded by petrochemical concerns, and when they set up climate institutes, they had Shell funding them and things like that. So there's a mix of governmental funding, some military concerns, some industrial concerns, etc. That enables quite a lot of work across these different areas. It is shaped by political debates too, to some extent. In their correspondence, you see responses to the famines of the 1970s and the like. Those particular people, one of the things to note is that they stem from places that are responding differently, but similarly to the Cambridge group that I showed. Lots of groups are starting climate work in geology, etc. And several of them are doing it in oceanographic work, and they collaborate. And one of the things that's interesting there is Lamont Doherty becomes the core depository, whereas the cores from the first ship were carefully parceled out by the person who led that, a Swedish scientist, to different people, getting different arguments from different areas. So you can actually plot the way these changed over time, and you can see some elements of different funding structures, etc., in the way that they emerged. So lots to investigate there. Yeah.
So, thank you. Let's see if we have another question. Perhaps I can follow. Okay, Michael.
It's a fascinating analysis. I think one theme that you've really highlighted very strongly is the role of the reappropriation of data, infrastructures, institutional forms, communicative forms, and I wonder if there is an insight we can take forward historiographically from this workshop about the relationship between appropriation and modeling as a way to understand a particular kind of mathematical or sort of mathematically involved activity.
Yeah. So what I would say on that is I think it's important not to see models solely technically. I think it is important to look at them in their technical innards, but it's also important to look at the model of social and economic relations that they stem from, etc. And many of those things feed into the way that they're interpreted in interestingly important ways. I haven't talked about temperature being a key parameter because you can use it in the economics and for fossil fuels, and you can use it in the climate. So it becomes a linking term in these arguments. I didn't mention fully, but one of the things that's really important for understanding the climate science denialists is that many of them are inspired by the model of the social world offered by Friedrich Hayek, which draws a strong distinction between the academy, which is inclined towards socialism, and public opinion, which is what you need to work with in order to affect politics, and provides a sort of map of American republicanism over the past couple of decades. And I think that really is important, and interrelating those is really important in this. So that's one kind of answer, but I'd love an answer that also moved into the different form of politics that's involved in these collaborations, and seeing that as political too. And you can see some elements of that in the gender politics of Emiliani and the like, and the way that his geological picture disappears from these people who can curve match better than he can, and so on. Yeah.
So let us thank again Richard for this terrific session.